Good morning, good afternoon, or good evening, depending on where you are. And thank you for taking time out of your day to join us for the AMETEK Solid-State Controls charge webinar, How Do Rectifiers Work? I'm just going to go over a few introductory things while everybody joins the room. So the first question I always like to ask is, can everybody hear me? If you can hear me, please type something in the chat bar to make sure I'm not just speaking to myself. That would be very helpful. My name is Craig Williams. I'm the Senior Technical Manager here at AMETEK Solid-State Controls, and I am located in the Stafford office, which is just outside of Houston, Texas. Thanks, everybody, for letting me know you can hear me. I've been working in the industrial UPS industry for 20 years. Goodness gracious me, where has the time gone? 20 years. As you can tell from my deep South Louisiana accent, I'm not from around these parts. I was originally from Scotland, and I worked in the North Sea oil and gas industry, working on UPSs in the North Sea oil and gas fields. And I moved here about 8 years ago now. I've worked with all the major UPS charger manufacturers. I'm very familiar with them all. Regarding the webinar, there will be a lag of around 30 seconds. The platform that we use is called Webinar Jam, and it has to process the data and send it out to Android devices, iOS devices, and Windows devices. And that processing takes around about 15 to 30 seconds. So from the moment that I speak to the moment you hear me is around 15 to 30 seconds. So if you type in the chat bar when I'm saying something and you ask a question regarding what I'm saying, I'm not going to see that quote in the chat bar until 15 to 30 seconds after I've said what I was saying. Does that make sense? Anyway, so please bear that in mind. And what we tend to do for that reason is we'll leave it until the end of the webinar to answer any of your questions. So feel free to type in a question at any time, but we will get to the questions at the end of the webinar, unless I catch it while we're going through and I feel it's pertinent that we should answer it then. Webinar Jam has a panic button. What that means for you guys and girls is that if everything freezes and locks up on my end, I can press the panic button. That will close this room, automatically open a new room, and you will all be automatically invited back into that room, and we will take over from where we left off. If you have problems on your end, sometimes your audio drops out, or sometimes it can freeze in your browser. We've heard that you can just press the refresh button in your browser and things should start working for you. The webinar will be recorded. There will be two options for you. You can rewatch the webinar using a link that you will get as you registered for this webinar, or the best way to do it is wait and our marketing department, they turn the link into an MP4 and upload the video to our YouTube channel. And that's the best way to do it, because on the YouTube channel, you can fast forward, rewind, and pause. Using the link that Webinar Jam sends you, they treat it as a new webinar, and you've got to start from the start, and you cannot fast forward, rewind, or pause if you use that. Okay, so that's all the introductions from me. I think everybody is here, so let's get started. So today we're going to hopefully help you understand what a charger rectifier is, understand the major components of an SCR-based charger, discuss how controlled rectification is achieved, ooh, big words, and discuss SCRs and diodes and how they work. And then finally, we'll discuss feedback control. So it's going to be a little bit technical today, so hold on to your hats. So the first thing I would like to discuss is the interchangeability of the terms rectifier and charger. And in truth, let's get it out of the way. They are both the same thing, okay? They convert AC into DC. The only difference with a charger is it's usually is that it's going to have a battery connected. So that's why it's called a charger, because the DC is charging a battery. That is the only difference between a rectifier and a charger, is that a rectifier usually may not have a battery attached to it, but a charger will have a battery attached to it. And as it says here, its main purpose is to convert AC, alternating current, which periodically reverses direction, to DC, direct current, which flows in only one direction. And there are two main types of rectification that we'll discuss today, and that's half wave and full wave. And it's used to convert AC to DC to charge batteries and supply critical DC loads. Those loads can vary from switchgear, tripping and closing springs and logic circuits, ESD, emergency shutdown circuits, fire and gas, telecoms, and PA systems, and many more, to be honest. And it's also a component of any complete AC UPS system, because you have to convert the AC into DC, and then that DC has to be converted back into AC to feed your critical AC loads. Okay. And the major components within a charger, and we're only going to discuss the ones in red today because that's all we have time for, but you're going to have an input breaker, you're going to have a transformer, then you're going to have your rectifier bridge, and also the term SCR and thyristor are interchangeable, they're the same as well. There are snubbers, fuses, we don't have time to speak about that today. Then there's the filter circuit and the control circuit. And then the alarm circuit we don't have time for today either. So the red things are what we are going to discuss today. So here is a very simple single line diagram of a charger taken from one of our DCR chargers that we sell. You can see here on the left-hand side, your AC input here. That is usually going to be three-phase 480 volts in the US, maybe 600 volts in Canada. But that is your three-phase input. That then goes through usually an AC input breaker, then through a transformer, and then that transformer usually steps that 480 down, and then that goes into the charger portion or the rectifier bridge. Here we have AC on that side there, and magically on the outside of this part here we have DC coming out. Then that goes through this fuse, and this is a voltmeter and an ammeter that we have on the front of our chargers, and then that goes out to your DC output or your battery. Okay, so that is really the basics of a charger. Is that all you need? Can we go and have lunch now? No, obviously. I'm going to go into things a little bit more in depth than that. So let's talk about the transformer first. So the main purpose of the transformer is to step the grid AC voltage down to a level suitable for the DC output. Now, the majority of chargers that we deal with are connected to a 60-cell battery that needs to be float charged at around about 135 volts DC. And some clever cookie came out with a really, really cool equation for working out for a three-phase charger what the DC will be compared to the RMS AC input. I'm not going to tell you how it's derived. If you want to do that, I'm sure Google will help you, but it's this bottom equation here. And what it's saying is the volts DC is equal to 1.17 times the volts RMS coming in. So what that means simply is if you have a 480 volt primary going into the transformer in the charger, usually we step that down to about 130 volts AC before it goes into the rectifier bridge. And we'll explain this a little bit more in the slides coming up. Okay. The second important thing that a transformer does is it acts as galvanic isolation. And galvanic's a very fancy word, but what it means is there is no direct electrical connection between the primary windings on the transformer and the secondary windings of the transformer. You can see in this drawing in the bottom right here, we've got our primary windings here, and they're wound around the core, but they do not touch the output windings. There is no direct electrical connection. Current cannot flow through this cable all the way through into this cable over here. It's impossible, okay? And what that does is it allows us to have some noise immunization. And what it also helps us do is the output for us is actually the rectifier bridge. We have our AC going into DC. So let's say you had a fault on your charger and DC managed to get back onto this winding here. Well, DC cannot pass through a transformer. It has to be AC. So what that does is it prevents DC from propagating over here on your AC input, which will be connected to your MCC. So therefore, this transformer will not allow DC to propagate onto your AC, and which could give you serious problems. So that's the two reasons we use a transformer in our design. So the next component we're going to talk about is the rectifier diodes. And diodes are semiconductor devices with a PN junction, and they only allow current to flow in one direction. When the anode is more positive than the cathode, then current will flow. If the cathode is more positive than the anode, then current will not flow. Okay? Now, unfortunately, electricity is invisible, and it's been the bane of my life. I wish we could see it so people had a better understanding of how current flows, how voltage, current, how it all works together, but we can't. So I like to try and come up with some analogies that are mechanical that will give you a better understanding of how electrical or electronic components work. So the mechanical equivalent of a diode is a check valve. Okay, so you can see we have positive here and we have negative here, and the flow that is allowed is here. So that means, let's draw the symbol, that means our diode would be like this, and this is the anode and this is the cathode. Okay, so when we have positive pressure on this side here, what it does is it pushes against that clapper valve and it pushes it out of the way, and it allows current to flow through that way there. Okay, and that is the same with the diode. If we have a positive voltage on the anode of the diode, that allows current to flow all the way through the diode out to this side here, where that is more negative. And obviously, if the oil flow changed direction and went this way here, it would push against this clapper valve. The clapper valve would close here, and current could not flow through the pipe. And for us, it would be the electrical wire. And once again, with the diode, if you had positive here, current could not flow that way. That cathode blocks the flow of current. So that is how a diode works. Obviously, there's not a clapper valve inside a diode. It's all done with the PN junction. So here are some various different diodes. So we've got our electrical symbol for a diode here. And let's start with this top one here. This package here actually has two diodes in it. And if you could, if I could zoom in, which I can't do on this presentation, you can see there's a diode there and there's a diode there. But I've expanded this for you. And you can see that this terminal here is the anode for this diode. And this terminal here is the cathode for this diode. And then surprisingly enough, we still use this center terminal for the cathode of this diode. And then the anode for the other diode is connected there. And what that allows designers to do is save some space and save components. And in a rectifier bridge or in a static switch, actually, we can use these modules here to save space and to save components. This one here is a hockey puck diode. And this whole surface area here is conductive, and you can't see it, but on the bottom side of here, that has a metal plate as well that is conductive. This diode has to be sandwiched in between two heat sinks, and the heat sinks will then become actually live conductors, and you have to connect your cable to the heat sink, and the flow of power will flow through the heat sink, then through the diode to the other side of the heat sink if necessary. They are a little bit of a pain in the ass sometimes, especially when you need to replace them. But they are good for high power situations. And you can see here, once again, I can't zoom in. There's the symbol there, and it's actually, I'll draw it for you. It looks like that. And therefore, this is the cathode side, cathode there, and this is the anode. Okay. This is a stud mount diode. This side here usually has to be screwed into a heatsink, and then you can attach a cable to this side here. And on this one here, this is the anode, and this is the cathode. And then this one here is actually a clamp mount diode, and you get a special clamp that you can screw down onto a heatsink. This surface here still has to be connected to a heatsink with a special clamp, and you screw the clamp down this way into the heatsink, and that pulls down the diode onto the heatsink that way there, and then you attach a cable onto that one there. Once again, this is the anode for this one, and this is the cathode. And please do be careful when you are replacing diodes or SCRs, because the manufacturers make identical diodes and SCRs in reverse fashion. So you can, for example, buy this one here, and this is the anode and this is the cathode. You can buy a version where this is the cathode and this is the anode, and they look pretty much identical, and the part number will be the same except for the last number usually. So please do be careful when you are replacing diodes and SCRs to make sure they are connected correctly. Okay. So let's talk about how a diode can give you half-wave rectification. So on the left-hand side, we have our AC power going in from the grid. And for ease, this is a single-phase system. We're not going to talk about the voltages or anything like that. Just a single-phase system. So the AC comes in here. And don't be fooled. This is not DC here. This is also AC here. Okay, you have AC on the primary of the transformer, and you have AC on the secondary of the transformer. Okay, and then we have our diode here. Now remember, current will only flow when the diode has positive on the anode with respect to negative on the cathode. Okay, so if we go to this portion of the sine wave, okay, this is positive on this terminal here with respect to this terminal here, which means we are positive here with respect to this terminal here. So you can see the positive signs match up and the negative signs match up. So therefore, this diode will conduct for this portion of the sine wave. And you can see it is transferred. This is the output. So you can see that that part of the sine wave got through. But for this, let me just clear that actually, for this portion of the sine wave, this is now more positive than this. So now the anode is negative and the cathode is positive. And it's not going to allow current to flow that way. So that portion of the sine wave there does not transfer across to the output. It's missing. Okay, so when you have a half-wave rectifier, you are only getting one pulse on the output per cycle. Okay, and the big question is this DC? And I'll let you think about that for just a moment. Is that DC? Okay, suspense is killing me. Yes, it is DC. It's pulsating DC because the current is flowing in one direction. Okay, the amplitude is changing, but it just becomes, the voltage becomes higher and higher and higher. Okay, it doesn't go past the 0 volt line here. If it did, then it would become AC again. So absolutely correct. This is DC. It is just pulsating DC. So that is a half-wave rectifier. So now we're going to discuss a full-wave rectifier. And you'll have to rack your brains from when you went to school. This is basically what we call a bridge rectifier circuit, and this one here is absolutely identical. Many people get taught this bottom one at school, but you've got to remember they're just drawn differently. If you analyze the circuit carefully, you can see that they are both identical circuits. And industrial UPS manufacturers and charger manufacturers tend to use this top one here. So that is the one that I am going to discuss today. But please do remember that they are both identical. Okay? And we're going to talk about how the power flows through each side to make it full wave rectification. So for the red portion, where this is more positive than this, the power flow is through this diode here and this diode here. You can see through the thick, bold red lines and the arrows, the power will flow through that diode all the way through this way, down through the load circuits, and then it has to get back to the power source on the negative lead. So it has to go through this diode here and get back to the negative. And once again, that gives you your positive half allowed through to the DC side. Now, what a full wave rectifier does is it doesn't waste this portion of the sine wave. What it does is it rectifies that too, and it does that by the other two diodes. So now this is more positive than this for this portion of the sine wave here. And if you follow the blue line and the arrow, it goes up through this diode. Now, very importantly, that's still the same positive as it was for this diode here. So we flipped it above the 0 volt line. Very, very clever circuit. And then that comes back and we have to get to the other side of the power source here to get back to the negative. And that's what a full wave rectifier does. And the cathodes obviously block the power flowing in the wrong direction for different parts of the cycle. So we have taken a full AC input here, and we are now getting 2 pulses per cycle. We're getting to utilize all of the voltage input on the output. I hope that's clear. And sorry I'm going so fast, but it's we've only got an hour, so I'm going through as quickly as I can. Now we're going to blow your brains a little bit. Here's a 3-phase rectifier bridge where it gets a little bit more complicated. But you've got to remember here, really, it is just, if you took this circuit here, that is just a single-phase bridge, and we've just added another pack of diodes here. And I'll explain how they work. So we have our A phase here, our B phase here, and our C phase here. So let's pick a phase that is going to be more positive. So let's say A phase is more positive than C phase at the exact part of the cycle that we're going to analyze. Which diodes would conduct? Well, we just follow it quite easily. So this is going to be more positive here. It can't go down that way because there's a cathode there. Okay, so let me just clear that. So this is more positive than that. So we are going to go down up here. Now, once again, cathode blocks, we're not going to go that way. Cathode blocks, we're not going to go that way. So we go out here through the load circuits and back here. Now, this is the part that usually gets people confused. Which diode do we go back through? Well, we have to get back to this point here because it's the voltage on A phase was more positive than respect to C phase. So that means we would go back through this diode here and go back. And that would give us a positive going hump on the output of the circuit. And you can do that analysis for every single phase. Let's say B phase is more positive than C phase, and it goes up through here, and we go back, and we have to get back to C phase, so it goes through that way there. Let's say C phase is more positive than A phase. So you would go down, it has to go up here, along here, and we have to get back to A phase, which is this way here. Okay, there's 6 ways the power can flow depending on what part of the cycle you're in for a 3-phase system. So here is the AC input. What does the output look like? Well, what you can see is what it does is this waveform here is actually this waveform here rectified and flipped up. This waveform here is this waveform here rectified. this waveform here, is this waveform here. So basically it's like they took, it's like your kids when they draw a butterfly, they draw one side on one side of the paper, and then they fold it down the middle and fold it, and you get both sides of the butterfly when you open it up. That's kind of what happens with the rectification. This green one here is actually, because obviously power flow is not going to go down this part here because the next phase takes over. So actually this would be the output. The green is the resultant DC waveform from a completely rectified three-phase input to a diode bridge. So hopefully I explained that okay. But now, okay, what happens if the AC input changes? Because remember, this is our AC input. So if our AC input changes, then the amplitude here, I'm not going to do the calculation, but if that changes, then that's going to change the amplitude of our DC, okay? Which is going to be a problem. Because remember, volts DC is equal to 1.17 times the volts RMS. So if we had 480 volts going in and 130 volts on the secondary, it's saying that our volts on the output will be 152.1 volts DC if we used all diodes. Okay, and you can see that all of these are diodes. So it's going to, the calculation is that will be 152 volts. Okay, but you know, our chargers have a tolerance. Okay, we can go down to minus 10%. So that means our chargers should be able to operate with 432 volts going in. Now, the equation, the direct ratio, if it's 432 volts, if it's 10% on the primary, then it's 10% on the secondary. So that goes down to 117 volts. And if we use the calculation, 1.17 times 117 volts, that goes down to 136.9 volts. So with a change on the AC input, you can see that has a change on the DC output. And that is exactly the same if you have an increase on the input. Excuse me. If we increase the input by 10% to 528 volts, that means the output of the charger is going to be 167 volts. Okay, so that's a big swing. We've gone from 136 to 167. That's a 30 volt swing with differing inputs. And obviously, as a UPS or a charger manufacturer, we can't guarantee what the AC input is going to be to your charger. You know, nobody has exactly 480 volts. Some people have 460, some people have 490. We have no control over that whatsoever. So we have to do something to mitigate those changes. Because what is the main purpose of the charger? This actually confuses a lot of people. They think it's to supply the DC loads. It's to keep your switchgear trip and closing supplies on. That's not the main reason for the charger. The main reason for the charger is to charge the batteries. Okay, that's the main reason the charger is there. So the batteries are always charged just in case you have a power failure, then the batteries will continue to feed DC to your DC critical loads. So we have to keep these batteries charged correctly. And a 60-cell lead acid battery needs to be charged at approximately 135 volts DC. That's for a 60-cell system, 2.25 volts per cell at 77 degrees Fahrenheit. Always check your battery manufacturer's datasheet to make sure that that is the correct voltage for your type of battery, but that is pretty much an industry standard. Okay. So if we went plus 10% on the AC input, then a high voltage on the DC will cause excess water usage. And if we went low at minus 10%, a low voltage will cause sulfation of the plates inside the battery, and both cause battery loss of life. And batteries are expensive and they are a pain to replace. So you want to get as much life out of your batteries as possible. So we have to come up with a system where we charge the batteries at exactly the right voltage all of the time. And how do we do that? Well, we use SCRs. Now, SCR is a silicon controlled rectifier. They're also called thyristors. The two names are interchangeable. In Europe, they use thyristors. It's just like many things. A thyristor was actually a name that a manufacturer gave to their SCR, and it just caught on. So most people in Europe call an SCR a thyristor. But the real term for it is an SCR. And it means it's a diode that can be turned on. Now, it is very, very, very important to understand that it cannot be manually turned off. Okay, and we'll get into that in just a moment. But it is a diode that can be turned on, and it's turned on by sending a signal to the gate of the device. And it will only turn on when there is close, sorry, it will only turn off when there is close to no current flowing through it. The holding point that will be specified on the datasheet. And that is, in other words, the zero crossing point of a sine wave, when no potential across the anode and cathode exists. And we'll explain this a little bit more in detail. So here is the electrical symbol for an SCR. Once again, we still have an anode and a cathode. And if you took away the gate lead, it would look identical to a diode. Okay, but that is how you know you're dealing with an SCR, because we have a gate lead. And you can see here, there is a gate lead here, there is a gate lead here, and you can see these leads here. They're the gate leads. And once again, this bottom module here, this is becoming more and more common. There's the gate cathode terminals here. And you can see on the side of the SCR package, it tells you there's two SCRs in here, and I can tell straight away, this is the anode, this is the cathode for both of the SCRs, and there's the anode. Okay. And once again, here's a stud-mounted one. They're very, very similar to diodes, except for they've got a gate lead. So the difference between an SCR and a diode. Well, let's go back to the mechanical equivalent again. And this is where I start to struggle and use my imagination to try and show you the same kind of check valve operation for an SCR. So let's say that this red barrier here is the gate. Okay. Now, when the gate is closed, in other words, there is no gate signal, it doesn't matter what you apply to this diode. Current cannot flow because the gate is blocking it. Okay, so if you don't send a signal to an SCR, it will not allow power to conduct through it. Simple as that. Okay, and when you send a gate signal, the gate opens. And what that does is it says, okay, if you send a gate signal to an SCR, it says, okay, now you can behave like a diode. So once again, you still need to have positive with respect to negative. Let's draw the symbol down here. Okay, there's the diode. There's the gate signal, so it's positive. So it will allow, once you turn the gate signal on, it will allow current to flow that way, but it will not allow current to flow that way. Even though the gate has been opened, it just says now you're allowed to be a diode. Hopefully that explains the difference between an SCR and a diode. And there's one more diagram here where I get really, really in depth with how the SCR works. Basically, let's say the gate. So this is still the gate, okay? Has this mechanism here. So when current is flowing this way here, or fluid is flowing this way here, it pushes against the gate and pushes it onto this ledge, okay? So when you send a signal, it latches onto that ledge and it stays on. It's only when current stops flowing, so let's say current stopped flowing, so that means there is let's say there's 0 volts there and 0 volts there. There is no potential across the anode and the cathode. Then that will allow this spring to push the gate back off here and close the gate. And that's what happens. That is the only time the gate will close. You can't remove the gate signal because it's latched on now. It's only when there is no current flowing through the device, because there is no potential on the anode and cathode, that the gate will then self-close. And hopefully we'll explain that a little bit more on the next few slides. So, what is the most basic purpose of a valve? A lot of people don't seem to factor that into their thought process when it comes to SCRs and diodes. Well, the most important basic purpose of a valve is to control the flow of current. Simple as that. Just like a faucet, you can have it going slowly, or you can have all the water coming out as fast as you can. That's what the valve is doing. So here's a very simple SCR circuit that shows you what an SCR can do. So we have our AC coming in here, we have a lamp here, and we have an SCR here, okay? And we have our gate signal coming in here. And what you'll see on this section here is how the gate signal will affect the conduction. In other words, the current flowing through the lamp, okay? So what we're saying here is, let's say we turn, so remember the sine wave in each of these drawings, this one here, and this one here, doesn't change. It always starts at this 0 point here, okay? What does change is where the gate signal is fired. So we're turning on the gate signal right at the start of this sine wave here, okay? So that means all of the sine wave power gets through. Now, obviously, there's only one SCR here, so this never gets through. This is half wave rectification again. But all of that sine wave gets through, because every time right at the start of the sine wave there, we are sending a gate signal. And once you send a gate signal to an SCR, it stays on until you get to that 0 crossing point there. Okay? Now, on this second diagram here, we're not turning the gate signal on until just before halfway through the sine wave. So we're only allowing this portion of the sine wave through, okay? So let's say that is half of the sine wave. If you use Ohm's law, that will tell you that the lamp will only be half bright at that point. Okay, so we can it's basically, this is a very basic dimmer circuit for a light. So using an SCR. And then if you really want to dim the light, you can turn the SCR on very late in the cycle and only allow this tiny portion of the sine wave through. And then that will make the power go into the light even less, and it will glow even less. Okay. So that is a simple circuit, but remember, in every single one of these, the SCR doesn't turn off until it gets to the 0 crossing point. Now look, we turned the gate signal off here. The SCR does not turn off until there, or there. Because once you turn an SCR on, it stays on until it gets to the 0 crossing point. So hopefully that shows you a little bit of how an SCR can control the power in a circuit. So let's apply it to a rectifier. So here is a 6-pulse fully controlled rectifier. So that's an SCR, that's an SCR, that's an SCR. So we have 6 SCRs in this circuit, okay? And once again, let's do A phase, B phase, C phase. Let's say we're going to go A phase is more positive than B phase. And let's say we want to turn the SCRs on for those respective phases. So that would be this SCR here, because we would go out through that way, back through our lows, and we want to get to B this time. So that would be this SCR. And we would go up that way, and we would get back to B. And depending on when we turned both of those SCRs on in the sine wave would depend on how much power gets through. And that's what this diagram shows you here. So the middle diagram is our gate pulses, and you can see our drawn lines here up to the sine wave. So you can see the bottom one is the rectified output DC voltage, and the top one is the input AC voltage. And if you correlate them both, you can see that we're turning the sine wave on exactly at the halfway point in each of the phases. And that is what the output here would look like on the bottom. Okay. So we've talked about diodes, we've talked about SCRs. Well, let's talk about filling in the gaps. Okay, so we have, let's forget about this circuit. It's just another version of a rectifier. What we're talking about here is these points here, okay? There is a gap there. If you're applying this DC to a battery, that's not going to be very good for the battery, because what's happening, this is 0 volts here, and this is 0 volts here. And the batteries aren't being charged at a constant DC voltage. We need to find a way to fill in those gaps so that the battery gets charged at a constant DC voltage. And the way that we do that is we use an LC filter. L is for induction, C is for capacitance. So you can see on the left-hand side, this is our rectifier output on a single phase system before it goes into an LC filter. And what the inductor and capacitors do together is basically fill in the gap. So if I did that on the input, that's kind of what it's doing. But on this circuit here, because it's a sine wave, it's just doing that to the output of the system. But it's filling in those gaps. So instead of seeing that waveform there, we're seeing a much flatter DC output, and a battery would be able to tolerate that level of ripple on a system. Okay. Now, filters are used to reduce the amount of AC content being seen by the battery. High AC ripple is bad for batteries, especially for valve regulated batteries, because it causes internal heating of the cell. The filter consists of an inductance and a capacitance, and the inductor is in series with the battery, and the capacitor is always in parallel. The inductor is usually placed before the capacitor, and capacitors are just like a small short-term battery. They do have electrolyte inside them, and that does degrade with time and temperature. And most capacitor manufacturers recommend that DC electrolytic capacitors are replaced at least every 10 years, if not sooner. If the ambient temperature is hot, just like for batteries, that time period is reduced. And please do remember, DC electrolytic capacitors are polarity conscious. They cannot be connected in reverse polarity. You will have a very bad day if you do that. It will probably let the magic smoke out of the capacitors, and believe me, it's like a David Copperfield magic show when that happens. It goes everywhere. So really make sure you check, double check, and triple check your positive and negative symbols on your capacitors if you are replacing them yourselves. DC capacitors, when they fail, can explode or catch fire. So that's why we recommend they're replaced, because when they do degrade, their failure method can be exploding or catching fire. And it has happened on many occasions, okay? And also a degraded capacitor can cause higher AC ripple to be seen by the battery. Now, an inductor is just a coil of wire that's wrapped around an iron core. The coil opposes a change in current by storing electrical energy as current increases, and by releasing electrical energy as current decreasing. It's kind of like a transformer without a secondary. Inductors very, very rarely fail because they're just a coil of wire. And the only problem usually is if that wire went open circuit, and therefore that would stop the output of the charger getting to the battery and to the load circuits. And it's very, very rare for that to happen. Inductors very rarely fail. So we said we need to control the voltage for the batteries. So how do we do that? Well, we use feedback. Feedback is used in so many things. Excuse me while I take a drink. Feedback circuits are used in so many things these days. So my question to most people is, what is the most common feedback circuit that you use on a daily basis? And if you drive to work and you get on the highway, the answer to that question is usually cruise control. Okay, so this is the general block diagram for any feedback circuit. You have a reference signal going in here, then you have a controller that controls the system output here, and then you have a sensor that monitors the output, and that puts a measured output into the reference, and an error signal is then combined and sent to the controller again. And it's just a constant loop. It's doing this all of the time. Okay, so for cruise control, you set your desired speed at your controller, then that at your steering wheel, and then that sends a signal to the ECU inside your car, and then that will control the throttle unit and the engine and the gearbox to give you to make the wheel spin, and that gives you your speed. That speed is then monitored. Obviously, they have a sensor in the axle that monitors the speed, and that is sent back to the error signal, and then that gets sent to the controller if something goes wrong to say, hey, we need to do something about it. And obviously, if you're going up a hill, your speed sensor, your wheels are going to slow down. So your speed sensor is going to say, hey, wait a minute, our speed has gone down. We need to do something. So that error signal goes into the controller. The controller says, okay, speed's gone down. We need to increase the throttle. And increasing the throttle increases, tells the engine and gearbox to spin the wheels faster. That increases the speed, and once the increase in speed basically cancels out the decrease that we just saw in speed, we're back in equilibrium, and the feedback circuit has done its job. And once you get to the top of the hill and you go down, the wheels are going to start spinning faster. Okay, so the speed sensor says, oh, wait a minute, my wheels are going faster. Send the error signal back to the controller saying, look, we need to decrease the speed. So it says, the ECU says, okay, let's back off on the throttle. So our speed goes down, and once they're in equilibrium at that point there again, and that point there, and it says, okay, we're back to where we need to be. And that is exactly how our charger works. Okay, instead of setting our speed using the button on your steering wheel, we set our reference using the float equalize pot, or through in our digital systems through the screen. We set it at, let's say, 135 volts. Okay, then the control board says, okay, let's do what we need to make sure that the SCR bridge here puts out 135 volts. Okay, I'm just going to talk about the voltage sense. We're not going to talk about this today. I don't think we're going to have time. So the voltage sensing says, okay, I'm getting 135 volts. That gets sent back. There is no error signal because when we set it 135 volts. So everything's good. We are in equilibrium. Charger is happy. We've got 135 volts going out. But once again, what happens if our AC input goes down? Okay, that means the peaks of our sine wave are going to go down. So that means instantaneously our system output is going to go down. So our voltage sensing says, oh, wait a minute, for some reason our DC has gone down. I don't know what it is, but what you need to do is increase the voltage here. So the control board says, okay, I am going to phase the SCRs on earlier in the cycle. Okay, so let's say they were phasing them on like that originally for 135 volts. Now they're going to phase them on much earlier in the cycle. My drawing is terrible. I hope you understand what I'm saying. So they're going to turn the SCRs on earlier to get more voltage out. Voltage goes back up. The feedback circuit says, okay, we're now back at 135 volts. There is no error signal back here. And everybody says, good, we are all good. Okay, and that is basically how our charger control circuit works. It's always monitoring the output of the system here and making sure it stays constant with respect to the reference signal sent in here. And hopefully I can make that more clear by showing you this is actually a charger schematic diagram from one of our AMETEK SCI chargers. So you can see up here we have our equalize and float pot. That is where we set the reference. It's actually on this pin here. That is the cruise control button on your steering wheel. That's where we set the reference. That's where we are saying 135 volts. Okay. As you can see here, this is the control signals that go out to our SCRs here. Okay. And this is our system output voltage monitoring point. So that's monitoring the output, saying, okay, what is my output? And normally it should be 135. And just for reference, I've shown you here, there is a current shunt here that monitors the output current. But once again, I don't have time to go into that today. So let's see what happens. So let's say our input went low and it went down to about 450 volts, like in our example. Okay, so our input here has gone low. Then the DC output is going to go low momentarily. Okay, so what happens is this is the feedback cable that goes up here, and the sensing voltage says, oh, come on, guys, wait a minute, the output's gone low. So the control board says, okay, I need to send the gate signal earlier to increase the average voltage until we come back into equilibrium. Now, remember, at no point has the reference voltage changed. We set that either through the screen or through potentiometer. That doesn't change. It is only this sensing voltage that is changed. And it says, okay, I need to get back to where I need to be to make sure we have 135 volts on the output. And the same is true if the AC input goes high. If the AC input here goes high, then the DC output momentarily goes high. The sensing voltage says, oh, wait a minute, we're not at 135 anymore. We've gone up for some reason. Don't know why. So therefore, it tells the SCR to gate later in the cycle of the sine wave, which will decrease the average voltage until we get to a point where we have 135 volts here. And that feedback circuit is constantly working for every single cycle of the charger. It's constantly looking at the output, and it's always in that loop, and it's always doing everything it can to maintain the output at 135 volts DC. Okay, that is all I have. So any questions? I hope you all haven't just fallen to sleep or your brains haven't exploded with how fast I went through all of that. But obviously I'm going to stay on until everybody has asked their questions. So please, in the chat bar, type in any questions that you have. Now, just wanted to tell you while those questions are coming in, we are now back doing our training classes at our Stafford, Texas office. We actually have a training class this week, and that is full, and it's going on just right now outside this door. So if you are looking for more in-depth training on batteries, UPSs, and chargers, then go to our website and look for the training link, and you can sign up through that training link. Taylor's just posted it in the chat bar for you, so you can go directly through that link. We do a training course every month. Please do be careful about which training you choose, because we do the DPP training 1 month, and then we do our microfarad training the other month. So you have to make sure you know which UPS you have at your plant before you go ahead and book the training. But we have all our COVID restrictions in place. We've got plexiglass put up on all the desks. We're wearing masks. All the meals that we supply are individually wrapped. And it seems to be a roaring success. Everybody's glad to get back and do some training with us. Somebody has asked privately, can you do a demonstration of how to find working or failed semiconductors? I can, but it's one of those things that there is always caveats to how you do it. So let's draw an SCR, okay? And we've got our anode here and our cathode here. We tell everybody at our training class that an SCR or a diode fails short circuit 99.9% of the time. So the easiest test that you can do is get a fluke, put your fluke on resistance, and go from the anode to the cathode, okay? And if you get 0 ohms, then your SCR is bad, or your diode is bad. Now, obviously do it in both directions, but if it is a short, you're going to get 0 ohms in both directions. Obviously in one direction, depending on where you put your positive lead, if you put your positive lead on the cathode side, then you should read pretty much unlimited resistance. And if you put your positive lead on the anode side, it's going to allow current to flow through. So you will find some resistance there. I can't tell you what that resistance is going to be, but it definitely will not be 0 ohms, okay? So that is the easiest check for an SCR. All right, let's do an IGBT. So if you have an IGBT, in truth, near enough all IGBTs fail short circuit, and it's usually always between the collector and the emitter, okay? So the easiest way to check is to put a fluke once again, put your fluke red lead on the collector and black lead on the emitter, and if you get 0 ohms, once again, you know there is an issue. The problem with IGBTs is that they tend to destroy themselves when they get a short circuit. They're not very good at handling short circuit current, and they physically blow themselves apart. So you should look at the IGBT and look for signs of physical damage, and then what you'll see is an open, very high open in both directions. Some people say that you can send a signal using a fluke on the gate of IGBT, and then you can monitor the collector emitter and see if it opens and closes. Yeah, it can, but in truth, it's not pulling high current, so that's not proving that the IGBT is good. So for IGBTs, it's a bit more difficult, but for SCRs and diodes, pretty much 99.9% of the time, they fail short. Let's have a look. What is a typical connection of the input transformer? It is, I'm trying to figure out how we say it in the different countries. It is a delta Y in our chargers. So we usually always use a delta Y. And one of the reasons for that is we don't pull a neutral to our rectifier or charger. We only pull 3 phases using the delta transformer. We don't need a neutral wire. Obviously you need to run a ground, but you don't need a neutral wire for our rectifiers or chargers, because we use a delta input on the transformer and a star on the secondary, or a Y. Are all 6 SCRs individually controlled? No. Well, yes and no. But the SCRs are all switched on in pairs. So they are individually controlled. So yes, they have an individual signal sent to them, but they're usually derived from the same signal as the other pair, the other SCR that's being switched on. So it's a very good question. But they are individually gated, but the circuit does share certain points. I hope that explained the question, the answer. Let's have a look. Is there any more questions? No more questions coming in. I'm just making sure I haven't missed anything. What I would like to say as well is that we always send out a survey after these webinars, and the survey always asks what you would like us to discuss at the next webinar. We really look forward to hearing your suggestions, because that drives what we focus on for our webinars. You know, we don't want to just keep on doing what we want to do. We want to do what you want us to teach you about when it comes to our UPSs and chargers. So please do, if you get the survey, take the time to fill in the part that asks what you would like to be discussed at the next webinar. As Taylor's put in the chat bar there, if you need any assistance or have any questions, click on the link to the Solidstate Controls website, and you can contact us through there or via email at scimarketing@ametek.com, or you can also call the toll-free number 1-800-635-7300. Is there a document that shows that we have attended the webinar? Bob, unfortunately, I don't think we can do that. I will ask marketing if that is possible, but I don't know if we have been doing that. But I will get you an answer. So if that's everybody's questions for today, once again, I truly appreciate you taking time out of your day and spending it with us, going through this webinar. I hope it was interesting. I hope that you learned something today, even if it's just one tiny little thing. Then I think we have done our job in increasing your knowledge on how our systems work. It has been a pleasure speaking with you, and until next month, look for your emails and we will give you the date for our next webinar and what the subject is. So take care, have a good weekend, and thanks very much for joining us today.